This is sections 15.6 and 15.7 of Honors Algebra 2, Permutations and Combinations. How many different ways can the letters A, B, and C be arranged? Well, I could write A, B, C. That's one way. I could write A, C, B. Those are the only two ways in which A would appear first. I could write it with B first and then do BAC, or I could write it with B first and do BCA. Or C could go first and do CAB or CBA. And those are the only possibilities. So how many different ways are there? There's 6 different ways. And I wrote them all out. Well, each of these arrangements is called a permutation of the letters A, B, and C. Permutation, the order matters. The order of the arrangement matters. So let's say I had 4 letters. How many different permutations of A, B, C, and D are there? Well, notice back in the 3-letter example, 6 is simply equal to 3 times 2 times 1. Because when I choose the first letter, I've got 3 options. Once I pick that one, I've only got 2 options left for the second letter. That's where the 2 comes from. Once I pick those 2, I only have 1 option left for the third letter. That's where the 1 comes from. So when I've got 4 letters, I've got 4 options for the first letter. Once I pick that, I've only got 3 options left for the second letter. Once I pick that, I've only got 2 options left for the third letter. And once those 3 letters are all picked, I've only got 1 letter left. 1 option for that last letter. So just like we learned the other day, all I have to do is multiply these numbers. 4 times 3 is 12, times 2 is 24, times 1 is 24. There are 24 different permutations of those 4 letters. Am I going to write them all out? No thanks. Since this kind of multiplication happens a lot, we give the operation a special name. It's called a factorial. So a factorial is when we're multiplying a number by every positive integer less than that number. So n factorial is the number n times n minus 1 times n minus 2 times n minus 3 times n minus 4 all the way down to 3 times 2 times 1. So what we did with 4 letters up there, that 4 times 3 times 2 times 1, that was 4 factorial. 4 times number 1 less than that, times the number 1 less than that, times the number 1 less than that, till you get down to 1. For the sake of completeness and to make everything work, 1 factorial is just 1 times itself, so 1, which is 1. 0 factorial we define to also be 1, so that everything works and there's no contradictions. So know that fact. 0 factorial equals 1. Let's compute 5 factorial. Well, 5 factorial is 5 times 4 times 3 times 2 times 1. What is 5 times 4? That's 20 times 3 is 60 times 2 is 120 times 1 is 120. So 5 factorial is 120. In how many ways can the letters in the word justice be arranged using only 5 letters at a time? Well, how many letters are there in justice? There are 7. So for the first letter, I've got 7 options. Once I choose that first letter, I've only got 6 options. And then I've got 5 options. Then I've got 4 options. Then I've got 3 options. And then I've got all my 5 letters. I only want 5 letters chosen at a time. This is different than previous examples because I'm not using all 7 letters. I'm only using 5. So I've got 7 times 6 times 5 times 4 times 3. What is 7 times 6 times 5 times 4 times 3? Well, that's 2,520. This is a permutation. It's a permutation of 7 things taken 5 at a time, written with a little 7, capital P, and a little 5. A subscript 7, capital P, subscript 5. That's 7 things taken 5 at a time. That's what that notation means. 7 things taken 5 at a time. In terms of factorials, 7 times 6 times 5 times 4 times 3 is almost 7 factorial, except we're not multiplying by 2 and 1. So it's really 7 factorial divided by 2 factorial. So 7 things taken 5 at a time was 7 factorial divided by 2 factorial. The 2, notice, is just 7 minus 5. So in general, n things taken r at a time, the permutation of npr, n things taken r at a time, is n times n minus 1 times n minus 2, all the way down to n minus r minus 1. r up here was 5. So we took 7 times 6 times 5 times 4, and we stopped at n minus r minus 1. N minus 5 minus 1. 5 minus 1 is 4, n minus 4 is 3. So we stopped at 3. Well, if I just take that expression and I multiply the top and the bottom by n minus r factorial, then the top magically becomes n factorial. And it's not really magic. It works out algebraically. N times n minus 1 times n minus 2 times n minus r minus 1 times n minus r times n minus r minus 1 times n minus r minus 2 all the way down to 1. So that numerator becomes n factorial. So this becomes n factorial divided by n minus r factorial. So that is the derivation of the formula that we noticed up here. 7 factorial divided by 2 factorial is 7 factorial divided by 7 minus 5 factorial. So I've written that out down here. 7 things taken 5 at a time. 7 times 6 times 5 times 4 times 3 is 7 times 6 times 5 times 4 times 3 times 2 factorial divided by 2 factorial. If I multiply the top and the bottom by 2 factorial, well, that whole numerator then becomes 7 factorial, because 2 factorial was the missing 2 and the 1 that I needed to make 7 factorial. So it's 7 factorial divided by 2 factorial, where 2 is 7 minus 5. So 7 factorial divided by 7 minus 5 quantity factorial. Keeping up? Good. Number 3. The permutation of 4 things taken 4 at a time. Okay, well, according to my formula, it's 4 factorial. That's my n is 4. That's n. The second number is r. So 4 factorial divided by the factorial of 4 minus 4. Okay, well, what's 4 minus 4? Well, that's 0. Oh, no, I'm dividing by 0. No, I'm not, because we defined 0 factorial to be 1. So this is 4 factorial divided by 1, which is just 4 factorial, which is 4 times 3 times 2 times 1, which is 24. So notice, the permutation of 4 things taken 4 at a time is 4 factorial. The permutation of 5 things taken 5 at a time is 5 factorial. The permutation of 100 things taken 100 at a time is 100 factorial. All right? From a set of 9 different books, 4 are to be selected and arranged on a shelf. How many arrangements are possible? Well, we could do it as we've got 9 options for the first one, we've got 8 options for the second one, 7 options for the third one, 6 options for the fourth one. Or we can do it in terms of factorials. According to our formula, we've got 9 things permutated 4 at a time. 9 things taken 4 at a time. That's going to be 9 factorial divided by factorial of 9 minus 4. So 9 factorial divided by 5 factorial. Now, is that actually easier to work out than 9 times 8 times 7 times 6? No. But if you have big numbers, you can write it out like this, and then notice that, all right, if 9 factorial is 9 times 8 times 7 times 6 times 5 factorial, then I'm dividing by 5 factorial, I can cancel the 5 factorials and get the 9 times 8 times 7 times 6 that I need. All right? Well, what is 9 times 8 times 7 times 6? That's 3,024. There are 3,024 different ways that I can take those 9 different books, choose 4 at a time, and arrange them on a shelf. Well, it's an arrangement. That means the order of the books matters. Well, what if some of the books were the same? What if I didn't have 9 different books? What if some of them were the same? What if I had a couple different copies of To Kill a Mockingbird? So in other words, how many different permutations are there of, we'll take a simple example, the letters A, and B. So I've got 2 A's and I've got 1 B. How many different permutations are there? So before I had A, B, and C, 3 different letters, I had 6 permutations. Well, here, I can do A, B, do A, B, A. I can do B, A, and that's it. There's only 3. 3. So I cut it in half. Well, really what I did was I took the 6 from before and I divided it by 2 factorial. I'm not really dividing by 2, I'm dividing by 2 factorial, which happens to be 2. So this is really 3 factorial divided by 2 factorial. The number of letters I have, the factorial of that, divided by the permutations of the letter A, which are 2 because there are 2 letter A's. So 2 factorial. Does that make any sense? Well, here's the formula, if you just prefer the formula. In general, if a set of n elements has n1 elements of one kind alike, and 2 elements of another kind alike, and so on, then the number of permutations p of the n elements taken n at a time is given by n factorial, that was my 3 factorial from this previous example, divided by n1 factorial times n2 factorial, and you keep going for as many repeated elements that you have. So in other words, I had 3 letters, so that's my 3 factorial. I had 2 A's. So n1 is 2 elements of one kind alike. So that's 2 factorial. I didn't have any other repeated elements. So I just have 3 factorial divided by 2 factorial, which gives me 3 times 2 times 1 divided by 2 times 1. 2's and the 1's cancel, and I get the 3 that I had. Maybe another example will make that clearer. Find the number of ways the letters of the word hubbub can be arranged. H-U-B-B-U-B. Hubbub. Fun word to say. So there are 6 letters. So my n is 6. There are 3 B's. So that means in the formula n1 equals 3. And there are 2 U's. So in the formula n2 equals 2. So the number of permutations is 6 factorial divided by n1 factorial, which is 3 factorial, times n2 factorial, which is 2 factorial. No other repeated letters. The h only shows up once. So I've got 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1, divided by 3 factorial, which is 3 times 2 times 1, times 2 factorial, which is 2 times 1. Okay, well the 3 times the 2 times the 1 can cancel with the 3 times the 2 times the 1 on the top. That 2 divides into the 4 twice, and the 1 doesn't do anything, so 6 times 5 times 2 is my answer, so that's 60. 60 different ways that the letters of the word hubbub can be arranged. What do all of those examples that I've done so far have in common? Well, in all of them, the order mattered. We were arranging them, and we were arranging them in a certain order. The order that I arranged them in mattered. What if the order doesn't matter? So, for example, how many sets of 2 letters can be formed from the set containing A, B, C, and D? So I've got 4 letters, but I just want to form groups of 2. So I'm not ordering them in a certain way. I'm not saying how many arrangements of 2 letters can be formed. I'm saying how many sets. I just want to group them. Well, I can group A and B. I can group A and C. I can group A and D. Those are all the groups that contain the letter A. There are no other ones. I can group B. B's already been paired with A, so B and C, B and D. Alright, well now I can take groups that contain C. Well, C's already been paired with A and with B. That just leaves C with D. And then I can take groups paired with, or the groups that contain the letter D, but I've already got all those. D has already been paired with A and with B and with C. So how many different sets of 2 letters can be formed? Exactly 6 sets. 6 sets of 2. 6 subsets containing 2 elements from that set of 4 elements at the beginning. These subsets are also known as the combinations of the letters A, B, C, and D, taken 2 at a time. So permutations, the order mattered. Combinations, the order does not matter. That's the difference. We use similar notation to note combinations. We had NPR for permutations. We have NCR for combinations. NCR, the number of combinations of n elements taken R at a time. As in the example we just did, with the set A, B, C, and D, we had 4 elements taken 2 at a time, so we have the combination of 4C2, which was 6. Since order does not matter in combinations, there are fewer combinations than there are permutations, because some of those permutations get ruled out because they're just repeats of the same elements. So in fact, the very specific way that these numbers of combinations and numbers of permutations relate. The number of permutations is equal to the number of combinations times permutation of r taken r at a time. Well, that was just r factorial, remember. So the number of combinations of n things taken r at a time is the number of permutations of n things taken r at a time divided by the number of permutations of r taken r at a time. So that's just, remember the numerator was n factorial divided by n minus r factorial. This is r factorial. This just becomes n factorial divided by r factorial times n minus r factorial. So it's just like the permutation formula. Permutation of n things taken r at a time was n factorial divided by n minus r factorial. Number of combinations takes that same formula and just throws in an r factorial in the denominator. So it's not that much different, but it is making it a much smaller number. I'm dividing out more of those integers. So let's find the number of combinations of the letters of the word solve, taking them 5 at a time. So I've got 5 letters in the word solve. I'm going to group them 5 at a time. How many groups can I make? Well, I can only make one group. A group consisting of S, O, L, V, and E. Since the order doesn't matter, I've only got one group that contains those 5 letters. So there is one combination. Alright, how many combinations of the letters of the word solve can I form? By taking them 2 at a time. Alright, according to my formula, this is 5 things combined 2 at a time. That's 5 factorial divided by r factorial, so that's 2 factorial, times n minus r factorial. So 5 minus 2 factorial. That's 5 factorial divided by 2 factorial times 3 factorial. Okay? 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. The 3 that times 2 times the 1 cancel. 2 goes into 4 2 times, and this is just 5 times 2. 10. So that would be S and O, S and L, S and V, S and E, O and L, O and V, O and E, L, V, L, E, V, E. Those are the different combinations. Those are the different subsets of 2 that I can form. And I know 10 of them. In how many ways can a committee of 6 be chosen from 5 teachers and 4 students if, say, all are equally eligible? That means I don't need a certain number of teachers and a certain number of students. I'm just forming a committee of 6. So it's a committee. That means the order does not matter. So this is not a permutation. This is a combination, because the order that they're on the committee is not important. So if all are equally eligible, then I've got 9 things. I've got 5 teachers and 4 students, which makes 9. Taken 6 at a time. According to my formula, 9 things combined 6 at a time is 9 factorial divided by 6 factorial times 9 minus 6 factorial. That's 9 factorial divided by 6 factorial times 3 factorial. And working that out, we get 84. So if my committee is just 6 out of those 9 people, I can form 84 different committees, 84 different groupings of 6. But what if the committee must include 3 teachers and 3 students? So it's not just any 6, specifically 3 teachers, 3 students. Well, for those teachers, I've got 5 teachers total, and I'm going to form the number of combinations of 3 of them at a time. For those students, I've got 4 total, and I'm going to take the number of combinations of 3 of them at a time. If I just multiply those, that will give me the total number of combinations. It's just applying the counting principle from the other day. Number of possible combinations of teachers times the number of possible combinations of students gives me the total number of combinations. So that is 5 factorial divided by 3 factorial times 5 minus 3, which is 2 factorial, times 4 factorial divided by 3 factorial times 4 minus 3 is 1 factorial. Okay, well, 5 factorial is 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 2 times 1 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times 1. And I get 4. I get 10. 10 times 4, 40. 40 different ways. Here are your immediate practice problems. Number 1, in how many ways can the letters of the word special be arranged? Using all the letters or using only 4 letters at a time? Since we are arranging them, those are permutations. Number 2, evaluate the combinations of 9 things taken 4 at a time. Just apply the formula. That is the end of sections 15.6 and 15.7.